In this lecture, we are going to discuss the balance of potentials. Let us consider this configuration of 4 resistors P, Q, R, and S connected to a battery as shown. G denotes a center zero galvanometer. A galvanometer is basically an ammeter that allows current to pass through it in either direction. So in this case, either from B towards D or the other way around. It indicates the direction of current flow according to which way its needle deflects, just as I'm showing here. So for example, this deflection is showing a current flowing from B towards D. A deflection in opposite direction shows a current passing the other way around. This is called a null deflection, which means that there is no deflection in the needle, indicating no current flowing through the galvanometer. In this circuit, in fact, 3 different situations may arise. If the potential at B were higher than at D, so VB is greater than VD, the potential here is greater than the potential here, then a current would flow through the galvanometer in the direction BD. On the other hand, if the potential at B were lower than at D, so VD is greater than VB, then a current would flow through the galvo in the reverse direction, D towards B. And what if the potentials at B and D were equal? Then no current would flow through the galvanometer because the potential difference across it would be 0. The potentials at B and D are hence called balanced potentials. So as we're saying, PD across BD is 0, so the current through the galvo is 0. Balanced potentials may be achieved by adjusting one of the resistor values, say S. So if S is a variable resistor which can be adjusted, then it can be set such that the galvanometer reading gives 0. In other words, a null deflection is obtained because no current is flowing through this branch of the circuit. In fact, it is as if this branch were not part of the circuit anymore. In other words, with or without it, it doesn't make a difference if the potential at B balances that at D. Under such circumstances, therefore, we can deduce this, that the current through P, which I am denoting as I1, will be equal to the current through Q. And this is because at junction B, no current is flowing through the galvo, so all current is passing through Q. With a similar argument, if the current through R is I2, then the current through S will be I2, since at junction D, no current passes through the galvanometer, so current through R equals current through S equals I2. Moreover, the voltage across P is the same as across R. How do we know this? Don't forget that voltage is potential difference. So point A is a common point to both resistors. So the difference in potential between A and B must be the same as that between A and D, since potential at B is the same as at D. Same argument across Q and S. So voltage across Q equals voltage across S. Now the respective PDs are simply current times resistance. So here we have I1P, I1Q, I2R, and I2S. So from 1, I can write I1P equals I2R. From 2, I can write I1Q equals I2S. And if I divide both results, I get P on Q, which is equal to R on S. This result is showing us that if 3 of 4 resistors are known, then the unknown resistance can be found using these ratios of resistances. A practical form of the circuit just discussed is the slide wire, also called meter bridge. Resistors R and S are replaced by a wire AC of uniform cross-section and length 1 meter, which usually has a resistance of around 10 ohms. The advantage of this setup is that the ratio R on S can be adjusted just by changing the position of the movable contact D, called jockey. You must know the respective points A, B, C, D to help you understand that both circuits do function in the same way. So we have resistor P in between A and B, just like here. Similarly, Q is between B and C. R is between A and D. The point of contact that the jockey makes with the wire. And S is between D and C, just like here. And across A and C, we have the battery and a switch for convenience. Thus, if we had to apply the previous result to this situation, then we have P on Q is equal to R on S, but R now, being a length of wire, I can express it as rho L on A, length L1, which is the length of wire R, so the part AD, length L1, divided by the cross-sectional area of the wire. Similarly for S. Note that the resistivity is obviously the same, since it is the same wire, and also the cross-sectional area A, since we are saying that it has a uniform cross-section. The only difference is the length, which I'm denoting L2. So everything cancels except L1 on L2. So here I'm showing that the ratio R on S can be expressed very conveniently in terms of lengths, which can easily be measured with a meter rule. Moreover, if we denote L1 as L, then since the total length of the wire AC is 1 meter or 100 centimeters, then L2 will simply be 100 minus L. We can therefore apply this result to determine an unknown resistance. For instance, let P be a standard resistor of known resistance whereas Q is an unknown resistance which we would like to find out. Then all it takes is to adjust the position of the jockey along the wire until balance point is found, which means that the galvanometer shows null deflection, as I'm showing here. This is done more or less by trial and error. Length L, which is the length AD, is then measured with a meter rule, and hence Q can simply be determined using this result, which is obtained from here just by putting Q as subject of the formula. So Q is 100 minus L on L times the standard resistance P, which is usually around 5 ohms. Let's watch together this demonstration of the experiment.